Alright kids, here's another fun Mr. Bryant video lecture. I know you can't wait. So, all this stuff that we've been looking at involving forces and rotational motion and so on was first derived from our good friend and really smart guy, Sir Isaac Newton. A lot of the laws of motion that we've been looking at first were derived by Newton after he looked at the path of planets around the sun. So Newton theorized, just looking at the solar system and at the universe in general, that there must be some cause for objects to have a circular path rather than just a straight path. Based on his work and his analysis of the mathematics of celestial travel, we have the basis of pretty much all of modern physics. The gravitational force is what Newton observed. We've already talked a little bit about what gravity is. It's a field force that is exerted between two objects. All objects in the universe exert this force, and they exert it on all other objects in the universe. It's a straight-line force exerted from the center of one object to the center of another object. For example, your weight is a force that exists because the Earth exerts a force on you, on your center of mass. You reciprocate this force on the center of Earth's mass. These forces are mutual and equal. This is just an extension of Newton's third law of motion. All forces are met by an equal and opposite reaction force. And here's the formula, which really is the heart of Newton's law of universal gravitation. Fg, which is the gravitational force, which up to this point we've been referring to as weight, but can be used in other circumstances, is the constant of universal gravitation times the masses of two objects divided by the square of the distance between the objects. G is a constant of 6.673 times 10 to the negative 11th. Notice that this is capital G, not lowercase g. Lowercase g refers to the gravitational acceleration on a large body like the Earth, while G, big G, applies everywhere. So here's a problem for you to try. Let's say we have a 0.3 kilogram and a 0.4 kilogram billiard ball. How far apart are the billiard balls? Solve the problem, and then come back to this presentation. We enter in the force as 8.92 times 10 to the negative 11th. We have the universal gravitational constant times the masses of the objects on the right-hand side. Multiply both sides by r squared. Divide by 8.92 times 10 to the negative 11th. Then take the square root of that. And the two objects are 0.3 meters apart. Here's a few more to try. Solve them, and then carry on with the presentation. For problem number 1, pretty straightforward. Simply enter the masses of the objects and divide by the radius. So in this case, the force between the objects is 3.8 times 10 to the 12th newtons. For problem number 2, if we look at this particular problem, the forces between the objects are directly proportional to the masses. Therefore, if we cut one mass's value to 1/6 of what it was before, the force between them will also have to drop to 1/6 of its previous value. So that would be 900 divided by 6, or 150 newtons.